Okay, let's look at section 4.2. This section talks about congruence of integers. All right, so let's look at the definition. All right, so we say A is congruent to B modulo n if n divides the difference of these two guys, so A minus B, right? Which by definition of divisibility, so equivalent to, right, there exists some integer k such that, right, so the difference is a multiple of n, so A minus B is n times k, right? So that's the definition. Alright, so A is congruent to B mod n. Alright, so let's look at this example. Right, we have A, B, C, D, and N. They are all integers. Alright, so A is congruent to B mod n. Alright, C is congruent to D mod n. Alright, then we can conclude that the AC is congruent to BD mod n. Alright, so let's prove that. Alright, so the assumption. So in the beginning, I have no clue what to do, so I'm just going to write down what's given. Alright, so we have, alright, so we know that assume that A is congruent to B mod n, alright, which means by definition, right? So there exists some k, which is an integer, right? Such that the difference between A and B is a multiple of n, so it's nk, right? Then also the other hypothesis is C is congruent to D mod n. Right? This implies that there exists some integer L such that the C minus D is equal to n times L. Alright, then what we need to do is we have to show that the difference between AC and the BD is a multiple of n. Alright, so we need to consider, right, AC minus BD, right? So this is what we need to consider, so this expression. Right, so what we want to do is we want to somehow get n involved. Currently there's no n, so the way to involve n would be use these two equations. Right, first I'm gonna just solve for a. So if we solve for a, you get a is equal to, right, now you have nk, so there's some n there, and plus b. Right, same thing, if you solve this equation for C, you will have n times L plus D. Right? Right, so I'm going to substitute nk plus B for A and nl plus D for C and see what we get. So A would be nk plus B, right? And the C is nl plus D, right? Then you have to subtract BD, right? Right, then do just a little bit of algebra. So this is going to be equal to, right, so nk times nl would be n squared kl, right, and nk times d would be nkd, right? And b times nl is, I'm going to just put the n, oh, sorry, n b l, right? And b times d would be bd, so plus bd. Just multiply it out, right? And we still have minus bd, right? Which is very convenient because this is the only one which doesn't have n, but they're gone anyway, right? So you can cancel those out, right? Then you can see that here every single term has n in it, so I'm going to factor out n, right? You will have n, k, l from the first term, and you would have kd or dk. Maybe I'll write it as a d, doesn't matter, kd, right? And the last one would be n is factored out, so it's going to be bl, right? Right, so this implies that now we could write this expression as a multiple of n. So I'm going to call this guy m, right? So there exists some integer m, actually, namely, it's n, k, l plus kd plus bl, which is still an integer, right? Such that difference between AC and BD is equal to n times m, right? Right, so therefore, by definition of congruence, we know that AC is congruent to BD mod n, right? And that's the end of the proof, right? That's it. So this is a proof where congruence of integers is involved. All right, that's it. I hope that this was clear.